For those watching online, hello, I'm David. That's it, not that. I do that because people recognise my voice but not my face, because they've listened to my revision seminars and they can tell what the back of my hand looks like. Yes, but it is nicer when they see my face. So this is Maths 1A. For the recording, it's Maths 1A 2016. I've been asked to talk about summation notation. So I'm going to start with that, and then I'll stop the recording and start a new one for the next topic. Okay. Sum notation. I'm going to hopefully use this not just to teach you about sum notation, which I will, but also to teach you about how to attack learning a new notation of any kind. So when you learn a new notation of any kind, you should know multiple things about it. So let's see. You should know how to say it. That's always important, because then you can ask people about it. And you should know the rules for how it works. So, right, you should know how to know. You should know how to say it. You should know the meaning, and you should know the rules for how it interacts with all the other things you know. So, how to say it, the meaning, and how it interacts with other things. So if you ever see any new notation anywhere, maths or science or physics or engineering or anything like that, you should ask yourself those three things. Now, some people are embarrassed to ask how to pronounce things. Can never be embarrassed to that in the Maths Learning Centre. But if you feel that way in a lecture, then you may just listen very carefully to how they say it. You can always ask what something means. It is never bad to ask that, and I like to keep lecturers on their toes by asking them that. And then how it interacts with other things is the most important thing you need to know about sum notation. Okay? Not just what it is, but how it interacts with plus, minus, times, divide, and other sums. So that's what I'm going to talk through. Okay, so I might as well do them properly. No, not an X, sorry. It's just an example. Most people will read this aloud as the sum from I is equal to 1 to n of whatever that is, just so you know. Is equal to 1 to n of I squared plus 1. That's how you would say it. You might say the sum of I squared plus 1 from I equals 1 to n. It's grammatically correct rearrangement of that, but most people will read it with the things attached to the sum first. You don't say the word sigma, that's the name of that letter. You just say sum. Now that might seem a little bit stupid for me to say, but it's also allowing my brain to percolate on what I'm going to say next. So I'm just stalling for time, really. But it is very important to know how to pronounce things. A number of times I've had people come in the Maths Learning Centre and say, so what's this squiggle then? And then I point to the wall of Greek letters and say, that's the letter sigma. Okay. And what does it mean? So this is shorthand for something. So just like with any maths notation which has equal signs in it like this, we're going to be replacing these letters here with various numbers, and the fact that it's a sigma means that you add them up. So it means add up all the options for this when you sub in all these numbers. And so I think about it like this in my head, and I will actually write it on the paper usually. So if this here was not an n but say a 5, I would say when I is equal to 1, the answer is 1 squared plus 1. And when I is equal to 2, the answer is 2 squared plus 1. And when I is equal to 3, the answer is 3 squared plus 1. I is equal to 4, the answer is 4 squared plus 1. And when I is equal to 5, the answer is 5 squared plus 1. And I will add all of those together, and that is the answer. So that is how sum notation works. That's what it means. It literally means whatever you get when you add all those things together. And it's a shorthand that allows us to say, well, it's the same thing over and over, but the number's changing, so I'll specify how the number changes. Very important to realize that you're only allowed to use whole numbers here. By which I mean integers. Sorry, you are allowed to use negative integers as well. But you're not allowed to use fractions in that spot. And you have to cover every number between the bottom one and the top one, every whole number. You're not allowed to skip any. So if I wanted the odd numbers, I'd have to find a totally different way of doing this. So it's I equals 1 to 5. If I only wanted 1, 3, and 5, I'd have to find a different way of writing it. I'd have to cover everything between 1 and 5. That's important. But really, I can put whatever I want next to this, and as long as it involves, well, whether it involves an I or not, and I will take this and I will put in all the possibilities for what I is and add them up. That's what it means. And you can always go back to that. I should say, just for future reference, that while this one is a formula involving I, sometimes it's just a list of letters, a list of numbers that each have a name. So you might see it like this. Like that, where AI is a number, a letter A, it's the first one and the second one, or in case A2. So this would be when I is equal to 2, I get A2, and when I is equal to 3, I get A3. When I is equal to 7, I get crap. And I can't be bothered writing all the rest of them, so I'll just put dots in, which is how most mathematicians normally do it. Okay, you can always put dots in. That means that there is somewhere a list that says what A2 and A3 and A4 and A5 and A6 and A7 are, and they are whatever numbers they are. So those numbers could be anything. I mean, they could be complex numbers, really, if I wanted them to be. There's nothing that says that the A's have to be whole numbers, just the I's. Sweet. There we go. So sometimes there might be a function, and I can sub in I to figure out what the answer is. Sometimes there's just a list somewhere. And both of those are appropriate, and you're expected to be able to deal with either one of them. So that is that. Now we can get on to the good stuff. How do they interact with stuff? So, just like when you first learned, well, maybe not first learned multiplication, but early on when you learned multiplication, you learned about how it interacted with plus. So you knew that 5 times 10 is the same, 5 times 12 is the same as 5 times 10 plus 5 times 2. You could split apart numbers and do the multiplications separately. And that's the sort of thing we're going to do. How does this interact with plus, minus, times, divide, that sort of thing? And so here we go. Here are our rules. Rule number 1. It doesn't have to start at 1. It can start at any number I like. It's just an example. And I'm going to use AI to represent either a list of numbers or a formula involving I, just so that you can see how it goes. Basically, if I times it by a constant on the inside, it's the same as timesing it by a constant on the outside. That's sort of the first rule. And that's just the same as the multiplication rule for addition. Look, if I times them all by k first and then add them up, it's the same answer as if I add them up and then times by k. So I can do that. Anything, in fact, anything that doesn't involve an I can be brought out the front. Even if it doesn't look like it's a number, it will be a number if it doesn't involve an I can bring it out the front of my sum sign. So if you do the sums separately first, well, you could just as easily add them together first and then add the answers. So you can do this. It works in both directions. Most of the time it will be most useful starting here and expanding it out like this. You can actually imagine it as the same as expanding out brackets. This sum attaches itself to both of those things if you really want to. Technically it's not doing that. It's actually spreading out the whole sum and grouping it together in a different order. But you can imagine it as expanding out brackets. Just don't say it in front of a mathematician. So there you go. Very important in this one here that these sums here are in the same one. You can't have this one start at 5 and this one start at 1 and do this trick. They have to be the same. So that's important. They're called the limits at the top and the bottom there. So they're the basics. It works just as well with minus as it does with plus. Yeah. Also minus will work just as well. All right. So they're the very fundamental things. There are a few other neat little things that we can do with them too that are to do with just sort of being creative in the way we write stuff. So the first one is you can always split sums apart and do part of the sum first and another part of the sum separately. Split them into separate pieces. You can always do that. Just as an example, I'm going to put proper numbers in. I could do this from 1 to 10 and separately from 11 to 17. That's just an example of the rule that I'm getting at there. So I can split it and say, well, that's every I from 1 to 17. I can do the bit from 1 to 10, and I can do the bit from 11 to 17. I can do those bits separately and add them together afterwards. Because it's just addition, I can do it in whatever order I want. All right, that's a very important rule. Similar to that rule is being able to pick off the first or second one and start a little later. So if I had something like that, I could go, well, I could do I equals 0 separately and then do the rest of them like that. There's nothing to stop me doing that as many times as I want. Whoops, sorry. So they're just things about fiddling with which part you do first. I'll do a proper example in a minute, but I just wanted to have a list. And then the next one is a really fancy trick. It goes like this. And it's easier to do with an example. Okay, so if I have something like this, this is saying that I have to do this, I have to go I equals 3 and sub it in, and that'll give me A5. And then I'll do I equals 4 and I'll sub it in, and that'll give me A6 because it's 4 plus 2. And I'll keep doing that and I'll get all the way up to A equals 7 plus 2, so A9. So what I'm really doing is I'm adding up from 5 to 7. I'm not really doing it from 3 to 7. If I actually adjust that number there, I'm adding it up from 5 to 7. So you can always do that trick. Now that seems like a lot of thinking for something. I mean, it's a very nice trick. That seems like a lot of thinking. What we can do is you can imagine subtracting 2 here next to the I and adding 2 here. So I could go, well, I'd prefer it to be AI. If I take 2 here, I should add 2 here. So you can always adjust your sums like that. You can put everything in this part involving an I, you can put it up by a certain amount and put the other ones down, or you can put this one down by a certain amount and the other one's up. And that's a very neat way of adjusting your sum so it looks slightly different and it makes it easier to do. That's the final fancy trick. And you can do it in whatever direction you like. Finally, there are a couple of ones that you're supposed to just know the answer to. So, you're supposed to just know the answer to these ones. Oh, thank you. So if you add up I from 1 to n, so that means when I is 1, the answer is 1. When I is 2, the answer is 2. When I is 3, the answer is 3. So it's 1 plus 2 plus 3 plus all the way up to n. That adds up to this. You may see it written differently to that. It might be n times n plus 1 over 2. You can imagine it as n squared over 2 plus n over 2 if you prefer. So you are supposed to know that one. I'm not 100% sure if your lecturers expect you to know the next one, but it can't hurt. So if you add up I squared, you'll get an n cubed and an n squared and an n. This one will be divided by 3, this one will be divided by 2, and this one will be divided by 6, which is 3 times 2. Like that. There is another version of that, which is a sixth of n, 2n plus n plus 1, 2n plus 1, like that. For the purposes of Maths 1A, this one's more useful, the top one, because the time when you're going to be using this is doing upper and lower sums, and you normally have to expand them out anyway. So if you're going to be using this to do upper and lower sums, you usually have to expand out these things so that you can divide them by n later, and that one's already expanded out, so it's a little bit quicker. Might shave seconds off of your exam. This one, if you're doing number theory, it's very nice because it's already factorized for you. Anyway. Okay, so they're ones you just have to remember, and it's very important to notice a few things about this. They start at 1. They don't start at 2 or any other number. Technically, if they start at 0, you'll get the same answer anyway because you'll get 0 squared on the front. But they do start at 1. Okay. So some examples of using all of these might be in order. These are all my rules, but they're just some examples so that you can see how it's done. So there's 2 classic things that they'll ask you to do and that you might come across. So one of them sort of happens when you're doing upper and lower sums anyway. So I'm probably going to leave some of that because there's a whole seminar on upper and lower sums on the website already, but I might come back to it if you want me to. But I will do some of the other ones. So there's 2. There's ones where you've got A's and you're told what some of them add up to, but you're not told what they all each individually are. And there's another one where it's formulas and you're going to be using some of these things to figure out the answers. So let me do one for you. So suppose from 1 to 10 of BI, the sum from 1 to 10 of BI is, say, I don't know, 15, and the sum from 1 to 20 of BI is 12. Okay, so I've got 10 numbers all added together here, and they come out to 15. And I've got 20 numbers all added up together here, and they add up to 12. So some of them would have to be negative, because otherwise the answer couldn't get smaller when I put more of them in. But it doesn't really matter. So what if, let's do some finding. Find the sum from 11 to 10 of BI. That's one thing that we can do based on that. Sorry? 11 to 20, thank you. 11 to 10 doesn't make the slightest bit of sense. Find from 1 to, I don't know, that one. And just to make it really fun, that. Yay. So just so you can see how I'm working here. Right. So part A. All right, so this is from 11 to 20. I know what it is from 1 to 10, and I know what it is from 1 to 20. So I literally am imagining this in my head. 1, 2, 10, 11, 20. I know what this bit is, and I know what this bit is. So I want to know what this bit is from 11 to 20, so I'll go this minus that, and that should give me what I want. So that would be everything from 1 to 20, take off the bit from 1 to 10. Now that is similar to what I showed you before, but backwards. Okay, it works just as well with minuses as well as it does with plus. I've got the whole bit from 1 to 20, and then I'm going to take off the bit from 1 to 10, and that's going to leave behind the bit from 11 to 20. And I know what these answers are, 12 minus 15, and that comes out to minus 3. You're right. And I literally will think of this and I will draw this on my paper in my exam. Possibly my scribble paper, but, you know, whatever. I'm not embarrassed to show that sort of working in my exam, but then I don't have to do the exam, so you do what you think is best. Part B said this. 2bi minus 1. All right, let's see. Well, according to my rules of doing sum notation, I can bring my sum in and do each part of this separately. Like that. That's not an I, it's a 1. And then this bit, I don't have to do the 2 right now. I can do it after I've done the sum. I can bring that 2 out. Now I know what BI, the sum from 1 to 10 of BI was. That was 15 on my original bit of paper. And the sum from 1 to 10 of I is, well, if I equals 1, it's 1, and if I equals 2, it's 1, and if I equals 3, it's 1, and if I equals 4, it's 1, and so on up to 10, and so I'll have 10 of them. So this is 10. It's the sum of 10 ones. And so I get 30 minus 10, which is 20. So that's a key thing that I probably should have written down earlier. The sum from 1 to 10, the sum from anything to anything of a single number is however many of those you add up. And I will do an example because there's sometimes we can get that wrong. Okay, and my last one based on this particular one. The sum from 1 to 20 of B of the floor of I over 2. I did not mention, and there are, no rules for dealing with floors in this context. However, there is always the one rule that you can use, which is what does the sum mean in the first place? And just write them all out with some dots in it. You're always allowed to do that. So, there are no rules to help. I can go back to the definition of what it means. This would be B of... oh, crap. Can I change the question? I plus 1 over 2. Sorry about that. This is the danger of making these things up on the spot. Right. If only one could change the question when you're in the exam, that would be pleasant. I decide the question is this instead. Okay, so that would be the floor of 1 plus 1 over 2. That's what you get when I is 1. And when I is 2, I get 2 plus 1 over 2. And when I is 3, well, there's plenty of those, right? So I'm just going to just put some dots in. Sometimes you need to put a few extra in to figure out what the pattern is, but this might be enough to figure out what I'm doing. Maybe I'll do one more. B floor of 3 plus 1 over 2. Okay, plus dot dot dot. And then the last one would be, last couple would be 19 plus 1 over 2 and 20 plus 1 over 2. Okay. All right, well, let's see what that is. 1 plus 1 is 2, divided by 2 is 1, and the floor of 1 is still 1, so that's B1. Now, 2 plus 1 is 3, divided by 2 is 1.5, and when you floor 1.5, you get 1, because you always round down, so this is B1 again. 3 plus 1 is 4, divided by 2 is 2, and when you floor 2, you get 2. Let me just check the next one. 4 plus 1 would be 5. 5 divided by 2 is 2.5. Round that down to 2. Okay. And 19 plus 1 is 20. 20 divided by 2 is 10. 20 plus 1 is 21. Divided by 2 is 10.5. And round that down to 10. Interesting. So look what I've got. I've got B1 and B1 and B2 and B2 all the way up to B10 and B10. I've got 2 lots of the sum from 1 to 10. I've got 2 of these. Two of them, which comes out to 2 of the sum from 1 to 10 of BI. That's what this is. And I know what that is. That's 15. Brilliant. Whoop. So you can always write it out and add them up and see what you get. The key moment, though, is what you're, in this context, what you're looking for is the ones you were told. I was told 1 to 10 and 1 to 20. Conceivably, I could figure out 11 to 20 from those. You need to keep looking for the ones that you can see. Right, a couple more examples just to make final sense of that. Very simple example. The sum, maybe I'll put another number there. Yep. The sum from 6 to 15 of 4. I'm going to ask some very brave souls to attempt to figure out what that is and tell me an answer. I will not be able to tell if the answer's right until I figure it out, so just write down your answers. So you've got like, I don't know, 20 seconds, figure it out, talk to the person next to you and see if you've got the same answer. Okay, so someone going to tell me an answer? 40. Anyone got something different to that? 36. Anyone else? 36 is a very common answer to this, and I'm very glad someone said that because it can allow us to learn something. So, how did you get your 36?
6 from 15 times 4.
Yep. Okay, so I'll say that again. We went 15 minus 6 and then times that by 4. Now, that's a great strategy, but there is one very, very tiny thing wrong with it, and we all do it really commonly. It's called a Fencepost problem. It's a maths education terminology. We've got I equals 6 and 7 and 8 up to 15. And I want to know, and there's a 4 for each of them, right? 4, 4, 4, 4. So I need to know how many of these numbers there are and times them by 4, and that should give me the answer. 15 minus 6 will chop this one off. And I won't include the 6 because I've taken it away. And so that's why it actually has to be 15 minus 5. So if you look at how many numbers there are here, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There's 10 numbers here, but 15 minus 6 is only 9. So I actually have 10 4s. So the key thing to note there is that if you do have sums like this, don't take off 6 or whatever the bottom number is, take off the next number down because you want to leave the 6 in there. So just pointing that out here, that is actually 10 minus 5, not 10 minus 6. Right. Thank you, brave soul. Yeah, well, maybe not that much. So just a final one. Oh, actually, can I? Yeah, let's do that. Yep. Okay, that's what we're going to do. Excellent. So we have the sum from I equals 61 to 100 of 3 lots of I plus 1 all squared. There are many strategies I could use. I could expand that out. That would work. And then do each part separately, because I have formulas for all those things. Alternatively, I could adjust my sum over a little bit so that it's not 3 I plus 1 squared, it's just 3 I squared. So I could take a 1 from this I, which would make that go down by 1, and add 1 to both of these. And that's the same sum. Now let's just think, just check that we're getting the same answer. If I put 61 in here, I'll have 3 times 62 squared. That's the first one. My first one here is still 3 times 62 squared. My last one is 3 times 101 squared. My last one here is still 3 times 101 squared. I'm adding up the same numbers overall. I'm just writing them down in a different way. And that I can do. Well, if it wasn't a 3 there, I'd have the sum from 62 to 101 of I squared. I know what the sum from 1 to 101 is. I've got a formula for that. I'm going to have to start at 1, and it doesn't start at 1. So I can do that same trick I did before from 1. If I go from 1 to 62 and 62 to 101, currently I have this bit. That's the bit I want. But that would be made out of that bit from 1 to 101, and there's a formula for that, minus the bit from 1 to 61, and there's a formula for that. The reason I need to start at 1 is because my formula does. Yes?
Say if you didn't have a number 1, say if it was 2, would you add 2 or add 4 because it was squared?
Okay, so you're saying if this was a 2 here, like this? Yep. Yeah. And I make this an I. Yep. It's right. You're imagining what's happening right next to where the I is. So if this was I plus 2, I would take 2 right next to the I and add 2 to these. So it's not what you get after you expand it out, it's what you get right where the I is at the moment. Do you reckon that will help in the future? Cool. And the other reason that that's not going to work is if you expand it out, there'll be an I squared and a 2I, and who knows what to do with that bit. So if you expand out I plus 2 squared, it'll be I squared plus 4I plus 4, and there's another bit in the middle. And we don't know what to do with that. But my key is to focus on just the I itself, ignore everything else that's attached to it, and look close into the middle of the brackets and change that. That's what we're looking at. Good question, though. Very important to ask what would happen if. Okay, so mine goes from 1 to 61 and from 1 to 101, so I'm going to need to do this. I'm going to go everything from 1 to 101, that's all of this, and take off the bit from 1 to 61, which is this bit, and leave behind the 62 to 100, which is what this bit here is. It's that same trick again that we were doing above. We actually didn't remove the 62. So we didn't go take off from 1 to 62 because we wanted to leave the 62 behind. Yep.
From 1 to I equals
1 to 40?
Yeah. So I equals 62, and you take away the 62.
Whoop. Yep.
Can you order 60,
Ah, okay.
61 from 100?
Okay, so you're saying you've got 40 numbers there?
Yeah.
Okay, we do have 40 numbers there, but they're not all the same number.
Right.
So the key back, good, very good noticing. The key back here is that all of these numbers 4, they're all the same number. And so I've got 10 lots of this 4. In this one, there are 40 numbers here. There are definitely 40 numbers, but each number is different. The first one is 3 times 62 squared, and the next one's 3 times 63 squared, which is a bit different, and the next one's 3 times 64 squared, which is a bit different again. So because each number's a bit different, I can't just use the fact that there's 40 of them, unfortunately, as nice as that would be. But again, good question. I like questions, they help us learn. So, and I note that is not sarcastic. It's very easy to sound sarcastic as a teacher. There is no sarcasm in the Maths Learning Centre. I really like questions, so please do keep asking them. I can bring the 3 out of both of these. And now there's a formula for this. Now let's see, I'm going to need more space. It's n cubed over 3 and n squared over 2 and n over 6. The n is the number that it's at the top here. And then the next one is n cubed over 3 plus n squared over 2 plus n over 6. And I choose not to figure out what that answer is. I have a calculator here though, that might help. A School of Maths approved calculator, which has a weird screen that we can't see. Anyway, I'm not going to show you the calculation. Oh. One cubed divided by 3 plus 61 squared divided by 2. And the answer is 113,060. Awesome. Of course. Yep, there's definitely a multiple 3, which is a good start. Okay, and there you have it. That's using some of those sum notation rules. I have one more to do, which people ask me about a lot when it comes up in the assignments, and so I'm going to do it. What if you have a sum and another sum inside it? Nice. So this is a sum from 1 to 6 of the sum from 1 to I of j. Now, they won't necessarily always put brackets here. They'll just have two sums sitting next to each other, like that. But what that really means is that there is a bracket there. Okay. There are a couple of ways of dealing with this, but both of them are about understanding what the sum means. So I could imagine it as brackets and figure out what this is first and have a formula for that if I wanted. Or considering there's so few of them, there's only 6 of these things, I could figure them all out separately and add them up and see what I get. So I'm going to do that one first. So I have I equals 1, I equals 2, I equals 3. Yeah, 6 is too many. I'm not going to do that. Let's figure out what this is. All right. let's ignore all of that and look at my brackets. Well, the sum from j equals 1 to n would be a half of n times n plus 1. But my n is I, so that's what I'm going to put in. Like that. So what letters things are is less relevant to where they are in the formula. The fact that this is a j is not relevant because the j is going to be replaced with the numbers from 1 to I. And the fact that this is an I isn't relevant other than the fact that my formula normally has an n in that spot and normally has an n in this spot, and so I will replace the n I would have here with an I. So this is what is normally an n in that spot in the formula. Now, I don't like calling things by the name of the letter that it normally stands for, but sometimes it helps. And now I can do this. Now, I don't have ways of dealing with multiplication inside a sum sign. Sums do not interact with multiplication. They only interact with multiplication by a constant and with addition. So I'm going to have to separate that. I'll expand that out. And then according to the rules of sums and how they interact with pluses, I can do each of these separately. Like that. And finally, I can bring the half out the front of each of those. And now I can use my other formulas, because I have formulas. There's a formula for this. It normally has an n in that spot, and it would be a half of n cubed on 3 plus n squared on 2 plus n on 6 plus a half of n times n plus 1. Because this one is an I, not an I squared. And whatever that is. I don't know what that is. I can. Yep, can't be bothered. Apparently 56. Sweet. There you go. Just to prove that the other method really would have worked, I'm going to do that too. Or if I is 1, I would have gotten the sum from j equals 1 to 1 of j. If I equals 2, I would have gotten the sum from j equals 1 to I, but the I is 2 of j. If I equals 3, I would have gotten the sum from j equals 1 to j, and that would have been an n, would have been an I, but the I is 3. And I'm literally copying all of this and replacing the I with the numbers that it is. And if I equals 4, I would have gotten I equals 1 to j equals 1 to I, but I is 4. This one's the sum from j equals 1 to I, but I is 5. And this one's the sum from j equals 1 to I, but I is 6. And I could have copied out everything that I had there, this entire bracket, copy it and replace the I with the number that it is. Copy it, replace the I with the number that it is. Copy it, replace the I with the number that it is. And I could now have figured out what each of those things is if I wanted. I could have gone, okay, well the first one is just 1, it's the sum from 1 to 1. The next one is the sum from 1 to 2, which would be 1 plus 2. And the next one would be 1 plus 2 plus 3. And the next one would be 1 plus 2 plus 3 plus 4. plus 1 plus 2 plus 3 plus 4 plus 5 plus 1 plus 2 plus 3 plus 4 plus 5 plus 6. And then I could have just added them all up. So it looks like I have 6 1s and 5 2s and 4 3s and 3 4s. Ooh. And 2 5s and 1 6, which is not 56. I think I've done something wrong somewhere. And here you see David showing you how to deal with what happens if your answer is wrong in the exam. Right. It does 56. Okay, good. Good to check it multiple ways. I must have done a times somewhere instead of a plus, I reckon. That would have done the trick. I got like 200 and something, so somewhere I did a times instead of a plus. My calculator skills are fairly low. Graphics calculators, like, who cares? I can't make an ordinary one work, so like, what's the point of having a graphics calculator? I'm pretty good at mental arithmetic now. My wife, who's a kindy teacher, is way better at mental arithmetic than me. Mathematicians tend to be really bad at mental arithmetic. Okay, so that is sum notation. Before I turn off the recording and talk about something else, does anyone have anything else to ask about that is related in some way to sum notation? Even if it's something I said there that was confusing. Cool.